postdoc session. So we have 3 different presentations today, well, this morning at least for this session. The first 2 ones are given by people from the Hubert Curien laboratory, and the third one from the Symbiose laboratory. What is important is that at the end of this session, we will give an award to the best presentation, and the announcement will be on Friday at noon. The link, if you want to assist to see the announcements, the link is given on the website of the Interdisciplinary Week. So I think we can start with a presentation from David PALLARES ALDEITURRIAGA. I hope I pronounced it right. From Hubert.
Very good, actually.
And so David will give a talk on femtolaser micromachining. So I give you the floor. You will give more details. So 20 minutes presentation, and after that, more or less 10 minutes for the questions. So don't hesitate for the audience. If there's something that you do not understand during the talk, you can also use the chat, and Raphaël or I will stop David if it's really needed. If you can wait, then you can wait until the end of the presentation, of course. But then if you think it's really important, you can use the chat. Okay, so David, I give you the microphone.
Thank you. Well,
sorry, I forgot to say that. So you have 20 minutes. So just 1 minute before, I will start again my webcam and indicate there is 1 minute left. But then you can finish. You have time to finish.
Okay, understood. Well, shall I start? Okay, do you hear me?
Yeah, perfect.
Okay,
yeah,
I'll start. Well, thank you. Good morning. I'm David. I'm here to talk about femtosecond laser micromachining of various materials for industrial engraving applications. This is a small part of an ambitious project called Graphene that is being performed in collaboration with Manutech-USD, Gravotech, and Fiberchrist. And it's mainly focused on femtosecond laser engraving. Laser engraving attracts a lot of attention, given its contact-free nature, among several other advantages. And also, femtosecond lasers gives ultimate precision, cleanliness, versatility, and supreme quality if we compare with another lasers like nanosecond lasers. Here, we have an image of a femtosecond laser drill and a nanosecond laser drill, and well, it's obvious which one is better. That's why there is a huge interest in the application of this technology, the industry, luxury goods, and biomedical sectors. But of course, it is not so simple, because every time that we are working with a laser, we need to handle a huge amount of laser parameters, such as wavelength, overlap ratio, fluence, and so on. And also, we want to apply engraving into industry, which means that we want to apply it to an even greater amount of materials. So at the end, well, let's take into account that each material will behave to these parameters in a different way. So we have a chaos that we need to put some order, and that's why Graphene came to life, was try to perform a smart parameter optimization of price quality engraving for each of these materials. Of course, we only have 20 minutes, so we can start talking about all the materials. We haven't done that yet. So here we bring 3 different materials that are not the common stainless steel. He's already being very studied. Here we bring PEEK, which is a polymer, silicon carbide, ceramics, and sapphire, a crystal. Here we have performed the threshold study. Here are the results with the well-known D-squared method. We can see that pig is the smoother one, the one with less threshold, the lower threshold, sorry. And sapphire is the one with a higher threshold. Well, of course, here, given to time, we also need to zoom in one material, study it properly, and then compare with other ones. For given its wide interest in biomedical applications, we should pick as the one that will be further studied. Okay, good. Now we have materials. Now we should talk a bit about setup and methodology. For setup, it's easy. It's just a very typical common laser setup with a galvanometer scan with the parameters that can be seen below. Those are the fixed parameters, the ones that we are not going to change. And what will be changing in this first study? Well, we will play with fluence, repetition rate, and overlap ratio. Okay, now two interesting things, something very particular about this study, this methodology, is that here we will try to keep same irradiation time for each overlap. When we say irradiation time, what we mean is that the time that for one inscription the shutter is on is the same. It's not the same as processing time, because in processing time we have to take into account when the galvo is moving but the shutter is off, so it's not processing. Okay, and how we keep the this irradiation time for different overlaps? Well, what we will do is pick an initial, how to say, overlap, like 90%, for example, and then we will calculate another overlap whose irradiation time is half. So we just have to write 2 times, and we keep the same irradiation time. We can do the same with looking for 1/4 time, and write it 4 times, and so on. You get the point, right? So what's the second interesting thing here? Well, as this is applied to the industry, we will be playing with one industrial standard. So we will satisfy the criteria that all the squares should at least have 100 micron depth. And in order to do this, for each fluence, we will set the correct scan number to at least have this depth. Okay. Well, so we have now the methodology, and we start scribbling in the squares. Good. But what will we be measuring? What are the parameters of the inscription that gives information about the quality of the inscription? Well, depth, as we already told, the taper angle, which is a good indicator of how sharp are the edges, how step-like is our inscription, roughness, of course, and brightness, because it's very important in the industry to know exactly the color change that our inscription has performed. Okay, and of course, you know, time is money. So that's our most important parameters that we'll take a look. And voila, finally, this is our first sample of results for peak. We have a repetition, 3 different repetition rate. We have here 2 fluences, different overlap ratios. Okay. So now, what's the first thing that we can see here? Well, it's obvious that for higher fluence, higher repetition rate, and higher overlap ratio, the color is darker. That's the first thing. And for the second thing, well, if we take a look, for example, to this square, well, looks nice, smooth edges, good quality. We can even say that this initial waviness is somehow being like polished. It's lower, this waviness here. It doesn't have disappeared, but it's still here, but it's lower. But takes 5 minutes. Okay, we can give to the industry something that takes so long. So we need to reduce this time. Okay, what's the simplest thing to do? Well, we can just increase repetition rate. So in this case, bravo, now it takes only 2 seconds, but well, the configure reveals that there are a lot of thermal effects that have caused surface melt. The edges are damaged. There's also some material deposition on them. Also, the depth, the average depth has increased, giving all this damage. So I think it's better to look something in between or looking in a way to avoid this damage. Okay. And maybe we can get some idea taking a look at the depth data. Here we see a clear tendency to increase depth with repetition rate and overlap. But when we reach a critical value of 100 to 100 kilohertz, depending on fluence, these thermal effects start to occur, happens, and disturbs the measurements as can be clearly seen at higher, fluence. Okay, but if we decrease the overlap ratio, then, as we can see here in the at low fluence, even if we are working with 500 kilohertz, we don't get this this thermal damage. So it will be interesting to playing with a low overlap. That can also be seen here, where we have an increase of depth with the overlap until again a critical value, then drops again. Okay, same tendency. This can also be apologies. I mean, how do you change this? Well, it has to. Well, sorry. This can also be seen with the taper angle. Okay, the same tendency. If we we plot these two values, then we have this a low correlation that even if it's low, tells us some information like at high overlap ratios, we get low taper angles for same depth, which is something interesting because then we have sharper inscriptions, which is interesting. Okay, here are also results of the roughness. We see a linear tendency that increase with push repetition rate. There is an increment with overlap. Okay, as this is negative because it's the roughness change, we see that the polish effect that we're already seeing. So, okay, now that we have performed, that we have conducted this study, I think that now we can start to write something a bit more interesting, like our logo, for example. Now we have chosen relative low overlap, mid repetition rate, and the result looks nice. We can see that depending on the inscription, we can get some things at the cost of other things. For example, at 12 joules and 4 joules, we see that get a sharp edge because we got approximately the same depth, but this one is sharper, but the roughness is higher at high fluence, but times is less. Actually, takes the double of time with 4 joules for reaching the same depth. Okay. Now, if we take a look to the microscope image, we see that there are no detectable, no particular damage. There's nothing ugly. The result is good quality in both cases. And also, well, the confocal study also doesn't reveal anything in particular. So the result, it looks it's white and it has a good quality standard. Okay, Sapphire. What happens with Sapphire now in comparison with PIC? Well, first thing, the scan number increases. We require more scans, thus it takes more time. Also, we see that at high fluence and high overlap ratio, we have some defects, some debris here. Okay, that if we highlight with the microscope, we can see it here, but we see another thing about all of this fluence, which is these micro cracks here. There are micro cracks at the edges that are like reducing the interest of the inscription. So it will be interesting to get rid of this effect, and that can be performed by reducing the overlap. Okay, in such case, that's right. There are no longer micro cracks, but we see another thing in exchange. We see like a low resolution effect, like a like edges that it's caused due to the low overlap. As we are using a low overlap, the distance between inscription between lines is higher, and then we have this pixel-like image. Okay, so here for Sapphire, there is not a good candidate. We need to see what is best for our for a particular case. We need to perform a trade-off. Okay, and finally, silicon carbide. First thing that we see here is that it's a material particularly difficult to inscribe. Please take a look at 8 joules and 75%. It takes more than 100 scans, which makes that the elapsed time is 400, which is a lot of time compared to PIC. And also, please take into account that we are using 300 kilohertz. So it's material more difficult to engrave, but it's of course possible. And what's the interesting thing about this material? Well, here we have that for the same fluence, we have same color, then this one only change with overlap ratio. And please take into account that with PIC, we have more like a grayscale change, but here it's more like a color change. We have here some brownish tones that suggest that we should perform a proper color measurement, not only brightness. Okay, if we make a closer look, then we see that the edges are okay. Okay, we don't see anything there, like no micro crack, no other particular issue here. If we now take a look to the 75, we clearly see the color change. Also, there are here not the, how to say, the step problem, the low overlap problem that we have seen in the Sapphire. Maybe it's because that here we are writing several times. And another particular thing is this region of this colorized region that it's in the outside of the of the processed region. Okay, that is like forming a shadow and happens in all the inscription, no matter the overlap or fluence. Okay, so in conclusion, we have performed our first optimization protocol for at least 3 parameters for now. We have adequately applied, and for example, in peak, we found out that thermal effects melt surface, deformation taper angle, but we can try to avoid this by reducing the overlap ratio at high fluence and high repetition rate. And then this way, the effect is not so strong. Okay. In addition, in Sapphire, we have seen that there is a high overlap produced by, that at high overlap, we see micro cracks at the edges, but if we reduce the overlap, then we have a low pattern resolution that is also problematic. And finally, in silicon carbide, we see a growth change that is mainly dependent on overlap ratio. Okay, so of course, our task has not over yet. We still have a lot of things to do, and among our future steps, we'll be applying this protocol to other materials. So we plan to inscribe in gold, platinum, titanium, borough float, etc. Also, we should study more complex or more exotic laser parameters. We can try to use a top hat, for example, to have a square beam profile. We can play with bursts, polarizations. And finally, we also plan to collaborate with the Institute of Dioptrics to help us to calibrate this color change that we have noticed. Okay. And well, 19 minutes, so I think it's time to finish. Here ends my talk. Thank you very much for your attention. And if you have some question, I think that's the moment. Okay, thank you.
Well, thank you, David, for managing the time so well. And for this interesting presentation on unusual materials, on laser machining on unusual materials. Are there any questions in the audience? You can raise your hand by clicking on your name in the participant window. Okay, I saw someone. Yeah, Donata?
Yes, thank you for the presentation. I was wondering whether like you could tune the parameters. Well, I'm far away from this field, but I was wondering whether you could structure also multi-layers. So if this technique could be applied to multi-layers.
You asked me if PIC could be applied to multi-layers?
Yes, indeed, of different materials as well.
Well, that's also outside of my region because I'm only, how to say, I only burning the plastic. I am not performing multi-layers, so it's above my expertise. So I can't give you a proper question to that.
Okay, thank you.
Raphaël, you raise your hand.
Okay, yes, I have plenty of questions, but I don't want to, if somebody else wants to have questions, no problem. So I have a couple of naive questions. Maybe I'm wrong, but you didn't mention the laser that you are using. What is the laser source?
You have a point. Yes, sorry. That's a problem with the time management. It's a Ethereum dub laser from Faber-Chrys. It's actually a prototype, so I can't also give you many details, but it's a Faber based laser.
Okay, and the advantage? I guess it's a power laser. Can you comment a little bit about that?
Sorry, I didn't hear you well. What did I choose? Please rephrase the question.
Yeah, my question is, can you give us some details about the selection of the laser compared to other source of laser? I don't know, carbon dioxide and so on.
I see. Carbon dioxide. Well, if we play with carbon dioxide, we are not using femtosecond laser. So it's out of the question. Among different, how to say, about different femtosecond laser sorts, we can tell that fiber laser is very standard because they have a really high repetition rate and high power compared, for example, the titanium sapphire, that it's also very interesting, but the repetition rate is quite low. Here, we need really potent and strong lasers because repetition rate, it's important to have it have a high repetition rate because that will give us a low processing time, which is critical and very remarkable for an industrial application. Okay, I don't know if I've explained myself well, if you have understood it.
Yeah, yes, very well. If there is not other question, maybe I can ask some more. So your characterization of the sample after irradiation is based on a microscopy image. Can you give us more detail of the type of microscope you are using and the resolution? Do you have enough resolution to see all the detail on the impact of the laser on the surface?
Well, if we want to do a really good characterization, we should use a scanning electron microscope, but I think that's a bit over the top. So for this, if we are using a typical transmission microscope, nothing relevant, or a really typical one. And we are, for this image, okay, go back. This one. Okay. Here we have using like 50 times or 20 times augmentation. It's not it's not very highly augmented, but it's not necessary because here we are engraving something that it's, well, arguably big. It's not something very small. It's not just, it's not only in one hole. So with these magnifications, it's enough for seeing the, how to say, how's the final result. How much to say? Well, it is true that we were use a scanning electron microscope where we see new things, but as I say, it's a bit like we saying in Spain, it's like killing flies with a cannon. It's not necessary. I don't know if you have another question or something.
Yeah, maybe a last one if there is no other question. Okay, so in your presentation, you mentioned one of the critical points, which is the thermal effects. Okay.
Okay. Yes.
So you consider three different materials. One is a polymer. So we expect that the thermal conductivity of the polymer is not very good. Maybe you can comment maybe
Definitely.
about that. Silicon carbide, so far I remember, is a very good thermal conductor. But what about sapphire? So can you comment a little bit on that? And also, because in some way it's kind of surprising that femto laser suffer from this kind of thermal management. I guess they suffer much less than other type of laser. So can you comment a little about thermal effect and the selection of materials?
Well, for the selection of materials, we look for PIG for the medical applications. Sapphire, because there's also basically giving it high threshold. We wanted to play with a really complicated material. And silicon carbide, well, It's the first ceramic that we happened to buy, basically. So that's the reason that we also wanted to play with ceramic. For sapphire, what to say about the thermal effects? Well, I assume that these thermal effects have to do something with the debris that it's here. Maybe it's an over melting or something similar. We have tried to remove it with a cleaning, but it's not that simple. Okay. So what to tell? Well, let's say that in silicon carbide we haven't found any thermal damage, and there are no other damage that happens here. So, well, basically, I will say that the damage, the thermal damage, it's only mainly important in thick, but as you say, it's mainly given the huge, well, not huge, sorry, the bad conductivity that it has. Okay, I assume that they start to having some thermal decomposition that leads some carbonization, and I assume that as well, how to say, that this thermal effect, this decomposition, it's what makes this black color here in comparison with this gray color when we don't have such effects. Well, that's mainly, I don't know if you have asked you properly.
Yes. So you confirm that, in your opinion, there is a correlation about thermal effect and thermal conductivity, or it's more complicated?
Oh, absolutely. Absolutely. Yeah, I think so as well. We should talk, we should conduct more materials. That's the good thing about this project, that for a lot of materials we're using the same setup, and that's very interesting, because if you want to do some research, we have all of these experiments might have been performed, but with completely different setups, so it's a bit more difficult to really compare how all these materials behave. And that, I think, is that the good thing of this kind of research.
Thank you very much, and thank you for the presentation and the time you spent answering my questions. Thank you.
Yeah. We are running out of time. Sedao, you wanted to give a comment on the talk, or was it a question?
I wanted to just, good morning. I just wanted to give some support and to answer one question that's from Donata. That's for composite materials engraving, it's possible to do it by layer by layer, or it's possible as well, depending on the absorption, transmission. We can do engraving of underneath surface layers without touching the surface. For other questions, for other things, I stop here. Maybe we can discuss afterwards. Thank you.
Thank you for the information. Thank you, David, for your presentation and the answers to the questions. I think it's time to continue with a second presentation. The second presentation.
Hello.
Yeah.
Hello.
Erieta.
Can I share my presentation?
Yes, I think, David, you should stop. Yeah, okay. So Erieta-katerina KOUSSI will give the next presentation. So please switch on your camera and share your screen.
Yes.
She's a postdoc fellow from the Hubert Curien Laboratory, and she will continue. She will give a presentation still on laser patterning, but this time on textiles.
Yeah. Just I need to warn you that before my computer completely crashed and switched off, and I have reinitialized, but I hope that it won't stop now. So, okay.
Let's hope so. If we lose you, then we know that it will take time.
Yeah, and now I would like to switch off my camera.
Okay.
Okay.
Okay, so it's yours for 20 minutes, hopefully.
Yes. So, good morning to all of you. My name is KOUSSI Erica. For reasons of abbreviation, it's Erica. I'm a postdoc student, and I'm under the supervision of Sedao and Cyril Mauclair. Today, I would like to present you my postdoc project.
Sorry, we do not see your screen.
You don't see my screen?
No.
Partage. Confirmer, annuler. How about now?
Now it's okay.
So maybe if I put it like that? No?
No, it's fine, but we see the logos and not the pictures.
Yes, because I haven't.
Okay, it's fine.
Yes. So yes, my postdoc project is named Bio-Inspired Surface Engineering through Ultrafast laser patterning for textiles. So as you can see by the introductional pictures at the cover page, nowadays the textile industry tends to be more and more in agreement with nature and be in constant research of fabricating smart and eco-friendly fabrics. Some of the properties that impose these smart fabrics, let's say, are the long duration after washing and the maximum prevention of dirt. The latter implies special treated surfaces that permit the hydrophobicity or the oleophobicity. And by these terms, we mean that there is a property of repelling water or oil by the surface. For such kind of characteristics, the researchers have turned their attention to nature. So, until now, the materials that permit water repellent treatments, and they are widely used in the textile industry, are polymers that contain, unfortunately, these perfluoroalkyl chains and degrade in PFAs, PFOA, or PFOs chains, which, unfortunately, they are not biodegradable. In the place of this, the PET, the polyethylene terephthalate, or the PA66, the well-known nylon, there are polymers already existing in the market and in many materials and coatings, and they are urged to replace all the above mentioned toxic polymers that they are about, I repeat, to be retired by the market. So in this project, the general introduction will present thus the models of nature from which the researchers were inspired to create hydrophobic or oleophobic surfaces, the applications of the reproduced surfaces in the everyday life, and the analysis of the wattability terms. Following, the topic of my postdoc project will be introduced, and the first comparative study of the UV and ER irradiation for both polymers, PET and PA66, will be discussed. I will, following, continue by analyzing the further research that concerns the two beam interference for DLIP. Finally, I will quote all the first preliminary results and the future perspectives. So let's start. Many researchers, inspired by the highly ordered hierarchical structures encountered in nature, and they have attempted to reproduce them by progressively developing the science of surface engineering. With constant observation, they have mimicked some morphologies, designs, and materials presented notably on the lotus flower, the rose petals, the water strider leg, the butterfly wings, the dragonfly, or the peacock's feathers, etc. However, not only the hydrophobicity was observed in nature, but also the oleophobicity, noted equally in nature, like on filefish and shark skin, on springtails, or in brachiosomes present at the surface of leaf poppers. So all these unique properties were envisaged to build some potential applications inherent to superhydrophobicity, such as anti-corrosion, anti-icing, anti-fouling, anti-fogging, self-cleaning surfaces in the medical field, or oil-water separation. Similar to superhydrophobic applications, we have built some super oleophobic applications that concern that include the anti-oil coatings, oil-water separation equally, liquid microlens, anti-blocking, self-cleaning, or bioadhesion. So now let's explain all the wattability terms, the hydrophilicity, hydrophobicity, or superhydrophobicity, etc. All these terms can be defined and visualized by the tangent contact angle theta formed between the droplet and the surface. If the angle is an acute angle, we call the surface hydrophilic, while if it is an obtuse angle, the surface is hydrophobic, or even superhydrophobic if it exceeds the 150 degrees. And here we can clearly see the evolution from hydrophilic to superhydrophobic properties on the oil droplet and the water droplet respectively. So, to enhance the hydrophobicity, we have to pattern properly the surface and texture it with a nanoscale or with a micro and nano combination scale to become hierarchical structure. And this is really a challenge. To realize such a complex surface engineering, we can pass through physical treatments, mostly for nanopatterning or chemical treatments. But there is also the option to combine both physical and chemical treatments. Worth mentioning that a surface can be engineered to be superhydrophobic, and continuously some further treatments will allow potentially the oleophobicity. The opposite effect is always applicable, and an oleophobic surface is necessarily hydrophobic. So, after the general review and the fundamental understanding, now I can introduce the topic of my postdoc that concerns the surface engineering on polymers PET, on eco-friendly polymers PET and PA66, destined for fabrics and clothing purposes with oleophobic properties through laser texturing. At first place, these polymers will be tested under the effect of UV irradiation and ER femtosecond radiation. The targeted technique aims the interference of two laser beams through the luminous and dark bands that will create ripples directly on the polymer surface. The distance between two luminous bands or two dark bands respectively is called period and can be properly regulated by the angle theta formed between the two laser beams. This technique follows the formula that you see here, and it is called DLIP, direct laser interference patterning. After nanotexturing with laser, we will follow a chemical treatment for surface functionalization. The elaborated surfaces will be envisaged for firefighters' uniforms, ski clothes, army or policemen's uniforms, with the collaboration of Sofileta and Alpex companies. So the first experiments of this project started by conducting a comparative study for both laser beams, UV and ER, and for both polymers. By irradiating, we have thus ablated the surface by forming craters, which were continuously observed by optical microscope, as you can see, and the diameter of its impact was measured. By measuring the diameter of each impact, we were able to plot the graph, yes, and doing the linear fitting and comparing the terms with this formula, we can define the waste for each beam radius. For UV, it's 9.02, and for ER, it's 1883 micrometers. From after the plot and after the given images obtained by the microscope, we can conclude that for UV laser, the ablation is apparent even with one-shot experiments. And the ablation threshold observed for PA66 is 3 times higher than this of PET. For infrared radiation, the ablation it becomes through multi-photon absorption due to the one EV laser energy, that it is much smaller than the band gap of the polymer's bonds. And this can be attributed to the presence maybe of the chromophores in PA66, or maybe to the possibly higher molecular weight of PA66 over this of PET that leads to the formation of highly viscous molten material during ablation. Finally, as we can observe also by the graph, the ablation threshold for PA66 is 5 times higher than PET. Well, the observations continue with the same microscopy. For UV laser radiation, we have, and 5 pulses, we have acquired the images for both PET and PA66. For these samples, you can see that there are no defined edges after ablation for PET, while there are some clearly defined edges for PA66. For ER irradiation, the sample PET, we have used for ER irradiation and 500 pulses that we have plotted before. The observation was difficult for the SEM due to the high rates of charge accumulation. The morphologies for PA66, in addition, were so similar with this of PET, so we have omitted all the images for PA66 and we have included the PET images. From these impacts, we can observe that for a laser fluence smaller than 5.4 joule per square centimeters, there are no visible marks on PET. And at this lower fluence, the form is not clearly defined, fact that suggests a non-linear nature of the ablation onset. And in the overall, the size of the craters increases by increasing the laser fluence. Continuously, we have conducted some Raman analysis, and we have evaluated the spectra of PET and PA66 before and after UV irradiation. The tested samples had an average laser fluence at 2.3 joule per square centimeters, and their number of pulses were 5. So before, for PA66, before Raman radiation, we can distinguish two characteristic peaks that they are attributed mostly to CH2 asymmetric stretching modes. After the Raman irradiation, we can see suppression that maybe means the alteration of physical or chemical bonds. For the PET sample, before the Raman irradiation, we can distinguish some 3 characteristic peaks attributed to ring mode 8A of the aromatic ring, to ester, or to vibration of the benzene ring skeleton. And after the Raman irradiation, all these peaks remained unaltered and no changes were observed compared to the reference. So we do the same thing for the ER irradiated sample. We have selected those samples that were irradiated with 25 number of pulses in order to avoid the deep holes. To this analysis, now we have fluctuated the laser fluencies. So the 2 more characteristic peaks before Raman irradiation are at these regions, and due to the laser fluence increase, these peaks appear to be suppressed. For the PA66 sample, we have decided thus to optimize our analysis by testing now an increasing number of pulses and maintaining the ER laser irradiation at a moderate laser fluence of 8.9 joule per square centimeters, but still increasing the number of pulses. Here are the characteristic peaks. And now by increasing the number of pulses, we have also observed the suppression of the peaks as the laser fluence increases. So the general remarks from this analysis is that in ER femtosecond laser processing, the high energies need to be avoided. And for PET and PA66, the chemical degradation is apparent even when we have a moderate laser fluence. So by this project, the general remarks gained from this study are that the UV femtosecond laser pulses can create shallow and smooth craters on these polymers, in contrast to the infrared femtosecond laser pulses that tend to drill deep holes and induce probable surface degradation. However, both can be capable for microscaling texturing. As it is not possible to produce nanoripples with one single laser source, we need now to proceed to a further analysis, the DELIP technique, with 2 laser interference beam. And this will be the following project. The project of comparative study was only to test all the parameters and see the influence on both polymers, PET and PA66. Now, for the DELIP technique, we have implemented a Michelson interferometry setup. And here you can see the experimental setup and the optical path followed. After the beam splitter, the recombined beam ends to a camera where we have found all these interfringes, the patterns, and the images of these fringes are illustrated at different positions of the beams. We can observe that the pattern changes dependently to the beam's position, fact that can allow us to create patterns with exotic configurations. The coherence length of the arms between the beam splitter was extremely delicate, and it was equal to 0.7 millimeters, and we could easily lose the interference pattern. The period, sorry?
Just one or 2 minutes?
Yes. The period was measured roughly measured at 120 micrometers. So after the observation of the fridges, we have implemented now the sample. Before we have an objective lens with a magnification of 10. The sample under study and for the preliminary test is a silicon sample. And here are the zoom of the beam splitter and the sample that it is placed on the translation stage. So the first results after the illumination of the silicon illustrate the threshold impact imaged with an optical microscope. For this impact, we have set the density filter to attenuate as much as possible the energy laser, and we have minimized the duration of the shot as well as the number of the shots. The first elaborated image by SEM reveal a primitive form of ripples with delip. As the delip technique is proportional to laser wavelength and angle, we can intervene to angle according to this formula and minimize the scale of the periodicity. On the other hand, at the periphery, we can observe a potential existence of lips where the lambda periodicity is proportional to wavelength with low spatial frequency. Thus, the future perspectives envisage the mounting of a special setup where it will be possible to minimize the scale of periodicity by tuning and controlling rigorously the angle between the two interference beams. And once this goal will be achieved, we will be able to pass on texturing on polymers PET and PA66 and test also the UV radiation. Thank you for your attention. And I am sorry if I have exceeded a little bit the time.
No, it's okay. Thank you. So thank you for this very clear presentation. Actually, you answered the question I had on chemical irradiation. So are there any questions in the audience? You can raise your hand. Any question? Okay, so first question from Raphaël.
Yes, thank you for this very nice talk. I was curious, maybe I missed something, but okay, you try only on nylon or PET fiber, right? But fabrics are made of an assembly of these fibers. Do you think that will be a collective effect? How do you did you try to monitor the wettability on the fabric rather than on a single fiber?
The largest part of the fabrics, and they were destined, as I said, for uniforms, they were covered by polymer coatings. So if we manage to treat the surfaces properly and make the nanotexturing, we can apply this progressively to large surfaces. This is not something applicable at the moment. We are trying to small surfaces, but progressively and with chemical treatments, it will be feasible to apply it for large surfaces. And I repeat, not in all textiles, but in specific textiles that they are wear by firefighters, ski, sports clothes, uniforms, etc. I don't know if I have answered your question.
Yes. How did you measure the contact angle?
Well, the contact angle is not measured yet because we are still on trying to nanotexture the surface, and we haven't achieved yet the nanotexturing. My recent results concern the irradiation on silicon sample, and then after the same imaging, we have found the first nano ripples, if we can say that. So after that, we have to improve a lot our technique. And if we manage to nanotexturing with a controllable technique, then the wettability measurements will be, I think, in a Manutech laboratory, and they are special techniques. I haven't done this yet, so I cannot really answer you.
Okay, thank you. There's a question from Florence.
Yes. Hello to everybody. Erica, I have a question concerning the main issues that you are addressing by using DLIP technique. What are the scientific challenges beyond this? Is it just for nanostructuration? Is it to address chemical issues or something, or what else?
Yes. So the advantage of DLIP is that according to the formula, as I have shown you, we can control the angle between the two laser beams. So with the Michelson interferometry that we are using now, the angle is not well controlled. We have already mounted a system that we can control the angle between the two beams, and we are trying to minimize their angles in order to pattern and control the periodicity. So this is a scientific challenge. Then, as I have shown you, the pattern of interfringes changes regarding the beam's position. So we can create some exotic patterns dependingly on how we will place the beams, and we can minimize the scales, reaching at nano texture. Then the technique will be supplementary. We will apply some chemical treatments in order to functionalize the surface. But the physical treatments are so important because we can, as I said, minimize the periodicity by controlling the angle, and play with the position beams to create some exotic patterns.
Okay. Are there any other questions? We have time for one more question. No? Okay, so I will ask my question.
Yes.
So you showed that you had chemical modification for the polymers, especially for, which one was it? PA66, I think? I don't remember which one. You had one polymer for which you had chemical modification and not the other.
Yes.
Both polymers are also crystalline. So do you expect, we can expect an effect on crystallinity. So did you measure it? Is it important for the applications or not?
Well, maybe we should take into account the crystallinity as well and make some further measurements. For the moment, we have done only optical microscopy SEM and Raman, but in the future, if we manage to make some nanotexturation and we cannot find the desired effect, we can proceed to further measurements. So yes, it can be crucial too.
Okay, thank you.
Thank you. And okay, I'm glad because my computer is not dead. So
That's right.
I have finished my presentation. Thank you all for your attention.
Yeah, thank you for your presentation and for the answer to the questions. So I will give the microphone to, so yeah, you have clapping.
Yes.
I will give the microphone to Raphaël for the introduction of the third presenter.
Yes, so once again, good morning, everybody. So the next speaker is Donata Iandolo from the Symbiose Laboratory. And we're going to have a talk about cell monitoring in vitro TD bonds models. So Donata, if you can share your slide. Okay, it's very good. Okay, so you can start.
Donata, we cannot hear you. You have to switch on your microphone, please.
Yeah, I've just noticed that. Sorry. So it is my pleasure to be here today. Sorry, technical issues. So it is my pleasure to be here today, and I will guide you through a small journey in the field of bioelectronics, which is one of of my main themes of my background. So one of the latest achievements in the developments in the field of biomedicine has been the development of in vitro models, but also organ on a chip. They are in vitro systems that have been developed to emulate structural and physiological features of specific organs and tissues with the aim to achieve what is called a body on a chip. So therefore, to then be able to conduct physiological studies, drug screening, where we have all the organs and tissues that are connected, and therefore evaluating the effect of specific drugs at different levels within the organ, and also moving important steps towards the idea of having a personalized approach. However, in this field, a robust model of bone is still missing. And indeed, I mean, like, this is what we are aiming within the team here at the Symbiose unit. We are indeed looking at developing a robust model of bone where we can study the effect of the fluidic environment of that cells experience within the bone. Where we know that the fluidic environment is driving not only the removal of waste products within the in vitro system, but it's also providing a mechanical stimulus to support and induce stem cell differentiation. This has a number of further, it can be a model also of what happens, for example, when we are in the case of bed rest for patients that are immobilized, or if we think of space missions, or what it could be a tool to understand what is happening to the astronauts that are experiencing lack of gravity on their skeleton. So in the host lab, in the interim unit, they have been developing the culture chamber that you see in the slide, together with a scaffold made of calcium phosphate that allows to achieve a very regular flow within the system. However, what we want to achieve is to integrate sensors and highly specific and sensitive sensors within the system in order to be able to monitor the cell fate in terms of secreted biomarkers. I have listed some, but the list is not exhaustive, and we can think of monitoring a number of different biomarkers and cytokines. In this specific case, one example could be the use of organic electrochemical transistors as an example of a sensor. And the idea here would be to move towards the concept of a feedback loop, where we use the level of biomarkers as a tool to inform the system to adjust the fluidic environment within the chamber. However, we know that the state of the art in terms of monitoring is mostly relies on the use of biochemical assays like qPCR or ELISA kit, or the use of the nanostring technologies that are, of course, highly specific and selective. They give quantitative data, but however, they are endpoint measurements and are most of the time very expensive, and key to our aim, they are discontinuous. And this means that, we have to have, if we want to study several time points, this means that we have to have several samples, and we have to focus on specific time points. Instead, if we want to have a continuous monitoring of what's happening, for example, in our model, the use of a device that allows us to track more or less over time the secretion of specific markers is really would bring important information on the physiology of the system. In this direction, we have envisioned and have already anticipated the use of biosensors. These are made; they are composed by two components, so a biorecognition unit and a transducer. The idea here is that the transducer is basically translating the signal into an observable one that can be electrical, mechanical, or optical. And it is important here to highlight that they are, of course, highly sensitive. They allow for label-free monitoring. They are, of course, and this is why we are aiming to use them. They can be dynamic, so we will have a continuous input of information, and also they are able to operate in complex biological environments, and they would be not invasive to the system under study. And this is also important when we have the sensors really in contact with the, let's say, cells or tissues that we are investigating. I told you, I anticipated that I will guide you through a brief trip in the field of bioelectronics, and indeed the workhorse of bioelectronics is the conducting polymer P.PSS, which is a cytocompatible and biocompatible polymer. Its mechanical properties can be tuned, and they depend on the process that we will adopt to produce to coat the surfaces or to produce the devices. The chemistry can be tuned. They are endowed with optical transparency, as you can see in this wound healing assay in the video on the bottom right side of the slide. And most importantly, they are endowed with mixed conductivity. Mixed conductivity is an important feature of conducting polymers in general, because this means that the polymer that you see pictured here is able to conduct not only electrons or holes, depending on the specific polymer, but also ions. And these are important because they will change the let's say the conductivity level, and also the signal that we will be measuring. And more importantly, these polymers are endowed with volumetric capacitance, which means that we are able to use the overall volume of the film, for example, that we will be using. So once again, I mean, ions can penetrate, and this is the main difference if we compare the use of polymers with the use of a metal surface, where we have deformation of bilayer at the surface of the electrode. More specifically, in this project, I will focus my attention on the use of organic electrochemical transistors. There are 3 terminal devices you can see in this scheme in the slide, where you have 2 electrodes, gold electrodes. They are called the source and the drain, and we have a third electrode that can be made of various different materials. In this case, it's silver chloride, and we can have different geometries, and I will show you in a moment. So you can have both planar and vertical devices, as in this case. So the PSS forms what is called the channel material between the source and the drain, and when we connect the device to a measuring unit, the current that we will be able to measure, it's only how to say, related to the doping state of this of the conductivity, let's say, of the film that we have, that is composing the sorry, I put a no. Sorry, 1 second. Okay, so it's easier to follow. So the current that we are able to measure, it's only proportional to the conductivity of the film that we have. Instead, the gate is able to modulate the current flowing through the channel, and this is highly important for the characterization of the function of these devices. A number of such devices have been used, and in this slide I represent a number of different geometries, but also sensors that have been developed to target specific metabolites like lactate. As I was mentioning before, these devices can be produced in a number of different geometries, such as, of course, planar devices, but they can also be fabricated on stretchable substrates. They can be integrated into microfluidic units, and they can be produced also as 3D scaffolds, so based on the conducting polymer in the form of a foam, or in the form of fibers. What I was referring to before is the selectivity and the specificity of the devices is due to the surface functionalization of the gate or the channel. And these can be done by using, of course, antibodies or aptamers, and also enzymes. And we will see a few examples in the following slides. So during my Marie Curie fellowship at the University of Cambridge, I worked in the last part of the fellowship. I worked with Francesco De Cataldo, and together we developed a functionalization strategies that would allow us to monitor BMP2, which is one of the cytokines that is released by cells undergoing osteogenic differentiation. Here we developed as I mentioned, a functionalization strategies that relies on the biotin streptavid in chemistry to bind specific antibodies against our target analyte BMP2, and this allowed us to monitor levels of BMP2 that are similar to those that are used in vitro to induce stem cell differentiation. And as you can see from the transconductance graph, we can indeed monitor every and each step of the functionalization, which means that the system is highly specific and also very sensitive. Now, in the frame of a project, of the bonus project that is funded by the European Space Agency, I'm working with a postdoc at the University of Cambridge, Dr. Ying Fu, and together we are working at the development of 3 different sensors that will be integrated within the system that I showed you before, and they are targeting at sensing lactate, but also rankle as a biomarker of osteoblastic differentiation, and sclerostin as a marker of osteocytes. So the devices that we will be using will have these geometrical parameters, the ones that you can see in this mask. So this is only a mask that is used for the microfabrication of the devices. And the idea is to, what we have done so far has been to functionalize the gold electrode with horseradish peroxidase dispersed into a chitosan polymer. The following step will be to integrate the lactate oxidase that I was mentioning before, and that you can see in this slide, so that, I mean, like, we will be able to basically integrate the production of hydrogen peroxide by the lactate oxidase with the action of HRP, and so we will be able then to sense the lactate produced by the cells. So far, we have developed the sensor integrating only the HRP, and as you can see from these amperometric graphs, we are able to sense selectivity and specifically sense increasing amounts of hydrogen peroxide with a high sensitivity. Ying has also, Dr. Fu has also developed sensors targeting rankle. And in this case, we've used a different approach where we use an aptamer, a peptide aptamer against rankle. And in this case, we are functionalizing the surface of, still we are functionalizing the gate, but in this case, the gold substrate has been coated with a film made of pivot. BSA is used to block the, to avoid any specific protein binding. As you can see from this impedance graph, we were able to monitor increasing levels of rankle added to the medium. We are now working on the development of the other functionalization strategies, and so far the work has been done on planar surfaces, and so not on the OECD. So all the data that I've showed you are mostly characterizing the gold or the PDOT surface, but the aim now is to functionalize the OECTs and then integrate the OECTs downstreams to the culture chamber to be indeed able to evaluate the analytes or the markers secreted by the cells that experience different ranges of shear stress or flow velocity. And with this, I would like to thank you for your attention, and I will be happy to take any question.
Thank you for your very good talk. The paper is now open for a question. So if you have a question, please raise your hand. Okay.
I have a question. You have not well understood what is rank L in one of your last slides.
Sorry, and I also stopped sharing, so I will go back to the slide so that I. Okay, yeah, sorry. This is the beauty of like of cross-disciplinary research. In this case, we are targeting rankle, that is a cytokine, so a protein that is secreted by cells, in a number of cells, but in this specific case, we are targeting osteoblasts. There are if I take a step back and I just skipped through the slides. Maybe I went fast through this, but I go very at the beginning. Basically. So if we, the idea of this project is that, I mean, like so the starting point is that, I mean, like from, if we start from a mesenchymal stem cells, we can obtain a number of different cells, and every each cell has a specific secretome. So it will secrete a number of different proteins and proteins like cytokines that are used to communicate with other cells, to influence other cells and tissues functioning. And the idea here was to isolate a specific molecule that could be used as a marker of a stage of the differentiation of the stem cells that we add into the culture into the culture chamber. And we identified rankle as a possible marker for osteoblastic differentiation. And as I mentioned in one of the slides, also protegenin as a marker of osteocyte. Sclerosing as a marker of osteocyte. I hope that I replied to your question.
All right, thank you.
Yeah.
Karine has a question too.
Yeah, Donata, thank you for your talk. You gave the scheme at the beginning with your device, and so it's on a culture chamber. But I was wondering on the medium that you can use to do the measurements. Can you use the culture medium, any kind of buffer or real liquids like blood?
Yeah. So, I mean, like I didn't. So I go to this. I mean, like if we focus on the OECT, I mean, like in so here I didn't specify, but of course this is the electrolyte. But and a number of so these devices, and maybe I can go here. So these devices, I take two practical examples. So this device has been is an ion pump. And is used to, it has been developed by a previous colleague of mine, Christopher Proctor. And in this case, this device is used to monitor and also to monitor epilepsy, but also to release a specific drug that is, let's say, controlling the events, the spike in the neurons activity. So it means that, I mean, like in that case, in this case, or also, I mean, like in this other case where these OCTs are integrated, are put on the surface of the on the skull or on the surface of brain. It's basically any kind of medium can be used as an electrolyte, and also in Stanford they've been developing wearable devices that would measure analytes within the sweat. So you can think of saliva as a possible electrolyte where you can measure measure your target analytes.
Well, thank you.
Also very complex media, I mean.
Okay, thank you. Sedao has a question.
Hello, thank you for this talk. I'm not in the field, I'm not expert at all, but from a point of view of end user, I'm kind of interested to know this biosensing compared to the sensibility of the detecting resolution. Is that comparable, for example, if we study osteoblast differentiation, is that comparable to classical immunolabeling, fluorescence microscopy, trick and tracing, and then image analysis?
So thank you for your question, and thank you also for the answer before. That was very kind of you. The sensitivity varies a lot, and what is interesting with these devices is that, and specifically with the use of PDOT, although a number of different other conducting polymers have been developed specifically to be applied for sensing application with OACTs, is that, I mean, like they are really, they guarantee high performances, which means high sensitivity and high speed, for example, when they are used to measure neuron activity. In terms of sensitivity and specificity, the functionalization makes the difference, and also the geometrical parameters of the device would make a difference, and also the geometry that we would explore would change, how to say, the time frame that we would be able to explore and to monitor. So in order to answer your question, I don't have a specific answer. So we haven't compared our sensor to an ELISA kit as yet. But it is very interesting that we can modulate, or we can play with the geometry of the device to extend the dynamic range of the sensors, and we can also play with the functionalization strategy to indeed be able to have sensitivity to very high low concentration of the target analyte, as well as, I mean, like having a wide dynamic range. Yeah.
Okay. Sedao, you want to add something else?
Thank you. Yeah, may I have just one quick question there? So this from, if it's possible, otherwise I can ask afterwards.
Yeah.
No, we still have time for questions, so keep going.
Right. Okay. Thank you. Thank you, Chairman. I have a question then. For example, this is you are looking at this is a bone model osteoblast evolution. If say I have another topic, I want to check some protein developments, evolution or transformation. What's the way to find active cells that react, that detecting certain proteins, for example, alpha, beta proteins in human eye crystallines? What's the way to find active detecting media for the medium that I want to detect? That's the question. Thank you.
I try. So I try and give you an answer, but we can maybe take it later and we can discuss it further. And I would be happy to do so. So well, I guess that, I mean, like in so if you think of these specific devices, of course they have. I mean, they can be, as I was mentioning before, you can modulate the device performance by changing the geometry of the device. For example, I mean, if you want to distinguish two forms of a specific protein, you can use, for example, molecular imprinted polymer that have been used to as an active layer onto an OACT. But of course, you can also think of using aptamers that may recognize a specific form of the analyte protein of interest. Another step, of course, would be to pass, if one has the option, would be to couple the study. So if you want to identify the molecule of interest, of course, the idea would still to pass by a mass spectrometry analysis of your sample to identify maybe a potential target analyte. And then, of course, you would have to go through the developments of like all the possible different steps downstream that are downstream to this identification. So, I mean, in this case, I mean, like it's a sensing mechanism. What I've been showing, it doesn't allow to detect new targets unless maybe you look into more complex geometry or functionalization strategies. But I'm happy to discuss that.
Okay, we have one question from Maura.
Yes, hi Donata. I was wondering, do you have any spatial resolution on where your signal comes from? Like, can you detect local concentrations in your chamber, or is it an overall concentration that you measure?
So thank you for the question. So if you are referring to the in vitro bone model, no, indeed, I mean, like the idea, and one second, I go to the slide. The idea here instead is truly to and the geometry of the scaffold has been designed so that you have a very regular geometry and a very regular, hopefully a very regular distribution of the cells, so that every niche channel and every niche point of the culture chamber and the scaffold, and in this case, will be will be representative of the overall conditions within the system. So this means that indeed the sensors will measure an overall production of a specific target metabolite. And like something that I didn't talk about in this presentation, but you can also integrate within the chamber sensors that are able to monitor, for example, cell proliferation or differentiation by using impedance measurement. But this would be, we wouldn't target specific analytes. We would really measure the surface coverage and the ECM that the cells release. So it would be a very different, let's say, philosophical approach to sensing.
Okay, thank you.
Okay, thank you. Is there any other questions? So just for curiosity, I can ask a question myself.
Sure.
So the type of sensor that you are using is a kind of ISFET, right? Usually we detect functionalization by a change of threshold voltage, but in your case, it seems so what is exactly the signal that you are monitoring for the change? Because at a point I see a transconductance versus frequency, and another point a current versus
true. So what I showed here, indeed, and you're right. I mean, so what I showed here is the final characterization of the device. So these measurements would be the let's say the true or the gold standard characterization of an OACT. So where you report, and I mean, in this case, of course, we have different functionalization strategies reported in the slide, but generally what we do is that we measure the performances of the, so we do two different kinds of measurements. We measure the device performances using different voltages applied across the channel, and different voltages applied at the gate. And so this gives us a certain indication of the performances of the device in general. When, for example, we explore different geometrical parameters. So because we can play with the measures of with the dimensions, of the gate, we can change the thickness of the channel, we can change the width of the channel or the length of the channel. So every and each parameter has an effect, or the material of the different components have an effect on the overall performance. So all these measurements can be done to characterize the devices. And then we can also run, as in this case, a measurement over frequency. That, I mean, it's a method that has been developed in the last few years by the group where Dr. Yingfu was based before in Hong Kong. And this, I mean, it's it's a more elegant way to represent the device performances. So
in this case, in this case, what you see is a change of mobility, right?
It's a change. Yeah. Every time. Yeah. Yes. Sure. Sorry. Yeah. If you go back to the basically to the physics of the device, indeed, it's always a change in the mobility of the ions that has in turn an effect on the conductivity of the film. And of course, thank you for this opportunity. Whenever we functionalize the gate or the channel, we are somehow opposing a resistance to the free passage of ions, and this is somehow what we measure. So so I hope that I replied to the question.
Okay. Yes. Thank you very much. So I guess if there are no other questions, we can end up here. Okay. So I would like to congratulate all the speakers for the quality of the presentation, and to thank also the audience. We have a quite large audience, so thank you to all of you to participate. We know that it's not easy to follow such a presentation on video, and so I guess, Karine, if you are okay, the session is over.
Yeah, I just would like to remind everyone that there will be an award that will be given to the best presentation, postdoc presentation. And if you want to attend the award announcement, you can go to the website of the grad school, the interdisciplinary session. So the link is there. And then we meet you on Friday at noon, Friday the 15th of January at noon. Well, thank you to everyone. Well, it's okay for me. I think we can stop right now and have a break.
Okay, and the jury is going to deliberate. Thank you very much. Bye-bye.
Bye.
Bye-bye.